Today we are going to unleash design patterns and discuss how we can use them to build elegant and confident solutions. We can start with answering the question, what are design patterns? And as you can see, one does not simply explain design patterns without introducing the Gang of Four. So, who is the Gang of Four? Gang of Four are four authors of the book written about 30 years ago called Design Patterns, Elements of Reusable Object-Oriented Software. This is kind of Bible of design patterns. But what actually design patterns really are? I would say that they represent best practices that developers have refined over time and offering a proven way to tackle recurring design issues. What is a purpose? Firstly, design patterns enhance code readability. By using well-known design patterns, we create a common language that experienced developers understand. This shared vocabulary makes it easier for teams to communicate ideas clearly and quickly. Because when a developer sees a familiar pattern, they immediately understand the structure and purpose of the code, which reducing the time needed to understand it. Secondly, design patterns promote code reuse. Patterns provide kind of templates or blueprints to solve specific problems, which means you don't have to reinvent the wheel each time you face a similar challenge. By reusing patterns, we can leverage pre-tested solutions, saving time and reducing errors. This reuse leads to more efficient development process and helps maintain consistency across different parts of the application. Last but not least, design patterns improve maintainability. If you have well-structured code, it's easier to debug, extend and modify it. Patterns encourage developers to think about the bigger picture and design systems that are flexible and adaptable. In summary, design patterns are an invaluable tool in the developer toolkit. They provide standard solutions that enhance code readability, promote reuse, and improve maintainability. We can divide design patterns to three main categories: creational patterns, structural patterns, and behavioral patterns. Creational patterns focus on object creation mechanisms. Design patterns which belong to this category are, for example, singleton, factory, or builder. Structural patterns usually deal with the object composition. As example, from this category we can mention adapter, bridge, or facade. Last category are behavioral patterns. Those focus on object interaction and responsibility. Here we can name patterns like observer, strategy, or command. Here are the basic characteristics of creational design patterns. They abstract the instantiation process, making system independent of the object creation, composition, and representation. They use inheritance to vary the instantiated classes or delegate instantiations to other objects. These patterns offer flexibility in determining what gets created, who creates it, how it's created, and when it's created. They also encapsulate and hiding knowledge of these concrete classes used and hide the creation and assembly process of these instances. Let's start with one of the well-known creational design pattern called singleton. This pattern ensures that a class has only one instance and provides a global point of access to that instance. Singleton can be used, for example, in resource management, for example, database connection, when we need to maintain only one open connection for the database in the whole application, or configuration settings, where we have only one object per whole application, where we can access the configuration values of the applications. And, for example, logging. Single logger instance used by multiple components of the application. Here we have some diagram to better explain and understand the singleton design pattern. First, I would like to mention the diagrams used in this presentation come from the page refactoring.guru, which I really recommend you to have a look, as this is the best source of describing design patterns and sharing code examples in different programming languages I found on the internet. But back to the singleton diagram. Here you can see we have the singleton class, and once it's trying to instantiate the object or the instance of the singleton, you see we are checking if instance is null, and if it's null, then we are creating the new object of the singleton class, or if it exists, we directly return the instance. Now let's have a look at the Python code example how to use the singleton design pattern. As you can see, we have the class called singleton defined, and it has the underscore instance class variable set to the none. Then we are overriding the instance creator method underscore new, where we are checking if instance is still none or if it exists. If it doesn't exist, then we are creating the new instance, and later on we can just return the existing one or just fresh installed, but it's still referring to the same instance. And in the example of the usage, you see that we have the singleton one, where we are calling and creating the instance of the class as singleton, the same for the singleton 2, and then if we are printing the comparison of the singleton 1 and the singleton 2, we see that it's still the same object. Second design pattern from creation design pattern category I would like to cover today is abstract factory. This pattern provides an interface for creating families of related or dependent objects without specifying their concrete classes. It's ideal for systems that need to be independent of how their products are created. For example, we can use them in the UI framework, which supporting multiple teams, or UI components, different teaming libraries, or different manufacturing systems. If we have a look at the diagram for the abstract factory, we can see under the number 1 we have a product interface. This is a blueprint that defines what all products should look like. Any product created by the system will follow this blueprint. Then under the number 2, above and below, you see we have a concrete products. These are actual products that are created, and each of these following the product interface, but differing in the specific details. Then, under number 3, you see we have a factory class, also known as a creator. It has a method for the creating products. This method returns type which matches the product interface. The creator class focuses on business logic, and the factory method helps separate this logic from the details of creating specific products. Then, under number 4, we have a concrete factory 1 and concrete factory 2. These concrete factories are subclasses of the creator class. It provides their own specific way of creating specific products. Then, on the right, you see we have some client code. It's remain flexible and independent of the specific product variant, as it communicates with their object via abstract interfaces. Let's have a look at the Python code example for the abstract factory code implementation. So you can see we have some abstract UI objects like the button and the checkbox. Then we have the concrete implementation of this abstraction for the UI objects for the Linux operating system, and then we have the concrete UI object for the Windows operating system. So you see we have the Linux button, Linux checkbox, Windows button, Windows checkbox. Then you see we have some abstract factory defined, which has this abstract method for the creation of the button and creation of the checkbox. and then we have the specific concrete implementation of these factories for the different operating system for the Linux GUI factory, which create the very specific button for the Linux operating system or the checkbox. And we have the same for the Windows. So we have the specific Windows GUI factory defined, which again implements our abstraction of the create button and create checkbox methods with the very specific implementation. Then we have some client code. You see we have the create GUI method defined, which takes a factory as an argument, which basically needs to create this button, checkbox, and return it back. So in our application, let's say we are checking which operating system the application is running on. So if our application is running on the Linux operating system, then we are creating our factory object for the Linux GUI factory. Otherwise, if it's running on the Windows, so then we are creating the Windows GUI factory object. And then we are using our helper method, which just takes a factory as a parameter. So we are passing our factory for that specific operating system, and we are getting back our button and checkbox for that specific operating system. Let's move on to the next category, which is structural design patterns. And here are some basic characteristics of them, like a composition. These patterns emphasize how objects and classes can be combined to form larger, more complex structures. Or interface simplification, which means that structural patterns often focus on defining straightforward and efficient interfaces for complex subsystems. This makes interactions more manageable. Next one is like flexibility and extensibility. They provide mechanism to extend existing structures without altering their original code, thus supporting the open-close principle. And last but not least is encapsulation and abstractions. These patterns encapsulate detailed implementations and abstract the interactions. Now let's have a look at one example of structural design patterns category, which is adapter. Adapter allows objects with incompatible interfaces to work together by providing something called wrapper, or converting the interface of a class into another interface that a client expects. Imagine you are traveling abroad and you need to charge your laptop, but then you find out that it doesn't fit to a local power outlet. So what's your choices? You have to use something like adapter to make possible to your charger to plug there. So now let's talk about some examples where we can use adapter, like integrating legacy code with the new systems, for example, adapting an old payment processing system to work with the new API by converting all method calls to new ones, for example, or working with a different data format, so converting data read from an XML file to a JSON format for application that expect the JSON input, or different cross-platform development. Now, when we are looking at the diagram for the adapter design patterns, so we see under number 1 client, which is the code that uses the client, or known as also target interface, to interact with the objects. It remains unaware of the specific implementation details of the adaptee and the adapter. Then under number 2 you see our client or target interface, which defines the interface expected by the client. It represents the set of the operations that the client code can use. Under number 3 we see a service, or our adaptee, which can be an existing class or system with an incompatible interface that needs to be integrated into the new system. And then under number 4 is our adapter, which is a class that implements the client target interface and internally uses an instance of adaptee to make compatible with the client target interface. Now we can put it to some real life example, like let's say printing some data. So we have some user which needs to print the document. So we have the printer interface which has a method print which expects some data. And we have some adaptees which might be the laser printer or the inject printer, which have own implementation how to manipulate the data and print them in the specific way for, let's say, laser printer or the inject printer. Now, per different printer, we need to have defined its own laser printer adapter, let's say, which has a reference called adaptee to our laser printer and call well-known method by the client interface, which is a print data, and at the end it's basically preparing the data and call the print laser on our adaptee, providing the modified data for that specific printer, for example. And we can have the same for the inject printer, so we will need to have the inject printer adapter as well. Now we can have a look at the Python code example of the adapter implementation. So as you see, we have our adaptees defined. So one class for the inject printer, which has a specific method print inject, which expects some data in some specific format for the inject printer. And the same we have for the laser printer, which has its own method called print laser, which printing again the data which requires some specific format for the laser printer. Then you see we have a target interface for a printer defined in the class printer interface, which has a print method for the document. And then we have the adapter, which adapts the inject printer to printer interface, which is a class which is implementing our printer interface, and it has a reference to our inject printer and has a print document method implemented where we can do some magic to transform data to inject printer and doing the inject printing on our specific adaptee. And the same we have for the laser printer. Again, we manipulate the laser data some different way, let's say, and at the end calling them. And then we have the client code, which basically is interested to print the document, no matter where it's at the end printed, if it's on the laser printer or the inkjet printer. So you see in the example of the usage, so we are instantiating our inkjet printer and laser printer. We are also instantiating our adapters, providing the reference to our specific adaptees, and then we can just simply print our document, and we do not matter, how it will be at the end printed. So it's a work of our adapter to do the thing to convert the data to our specific printer. Next structural design pattern is called bridge. It separates an object's abstraction from its implementation so that they can vary independently. It's useful when both the abstraction and the implementation needs to be extensible independently. It can be used, for example, in the cross-platform UI development, where we need to separate the abstraction of the UI components, for example, a button, from its platform-specific implementation. For example, Windows, macOS or Linux, to allow the same UI abstraction to work across different platforms. Or next example can be database abstraction, where we need to decoupling database operations. For example, queries, transaction from the specific database technology like the MySQL, MongoDB, Oracle, or whatsoever, to enable the same higher level database operations to work with different database systems. Or device control systems, where we need to have a separation of the abstraction for device control. So like power on, off, volume control from the specific device type like the TV, radio, and so on. Now we are looking at the diagram for the design pattern called bridge. So you see under number 1 we have something called abstraction, where we have defined reference for specific implementation. And this abstraction defines some features. So feature 1 and feature 2, you see when you have the feature 1, it's calling our method 1 from our implementation, and feature 2 is calling actually 2 methods from our implementation. Then under number 2, you see we have our interface of implementation, which define the specific methods. Then under number 3, we have some concrete implementations, which actually implement this interface of the implementation and have the different methods how to tackle the things. And under number 4, you see we can also have the refined abstraction, which has some new feature, which is calling some new method from the implementation. Last category of design patterns are behavior patterns. Those define patterns of communication between objects. They also focus on how objects interact and distribute their responsibilities. They encapsulate behavior in classes, promoting flexibility and reusability, and also facilitate the changes in behavior without altering existing code. One of the behavior design patterns is observer. It defines one-to-many dependency between objects, so that when one object changes state, all its dependents are notified and updated automatically. It's used in implementing event handling systems, where a change in the state of a model notifies and updates the other objects. For example, we can use it in the event handling in GUI applications. For example, it allowing multiple components like a button, text field to be notified and respond to user action. For example, clicking or the key presses and so on, by registering and as listeners to those events. Or real-time data feeds, enabling applications like the stock market ticker, news feeds, and so on, to automatically update and display the latest information by observing the data sources that pushes updates when new data is available. Or logging and monitoring systems, allowing different logging or the monitoring components like file loggers, console loggers, network monitors to be notified and record events from various parts of an application as they occur. In observer diagram, you see we have under number 1 publisher, which holds some list of the subscribers and holds some own main state. And it has few methods like subscribe, unsubscribe, notify subscriber, and some main business logic. Under number 2, you see that, for example, in our main business logic, when we change the state, we are calling the notify subscribers, which basically iterate over each of the subscriber and calling the update method, providing some of the context or the data. On the number 3, you see the interface for the subscriber, which has the update method and taking some context. And then you have under number 4 or 5 some concrete subscribers, which implements that update method with some specific context and doing something with the data. And then you have the client under number 6, which creates some specific subscriber, and it has a publisher and subscribe the specific subscriber. And once all it happens, so it will get automatically notified. Last behavior design pattern we are going to cover today is strategy. It defines family of algorithms, encapsulates each one, and makes them interchangeable. This allows the algorithm to vary independently from the clients that use it. Use case can be, for example, in the payment processing system, where different payment methods, credit card, PayPal, etc., can be selected and interchanged at the runtime without altering the client code. For example, sorting algorithm, when we are allowing a collection of the data to be sorted using different algorithms like the quick sort, mega sort, bubble sort, and so on. Mentioned payment processing system, or compression algorithms, allowing a file to be compressed using different algorithms like the zip, rar, gzip, and so on. That's all I had for today, so thank you very much for your attention. And if you have any questions, so feel free to reach me out on email or the LinkedIn. So thank you and have a nice day.